Hello everyone, I'm Kubi, co-founder at Gattaca, and here with Lorenzo. And today we're going to talk about how essentially the entire preconfirmations and base sequencing movement is supercharging Ethereum with fast preconfirmations, access or democratized access to additional yield, and as well as decentralizing block production on the L1. So to start with, why do preconfirmations matter? Yeah, this one is straightforward, and most of us are very well familiar with this. It's basically cutting down or like no longer being stuck to the 12-second block time, so vastly improving UX for users. The other thing, so base sequencing itself describes this. The base layer no longer is just a DA for rollups, but additionally, it actually has the capability of being a sequencer. So again, very well explored. The other factor, or the other thing that preconfirmations bring to Ethereum is actually access to additional yield. And specifically, if the market structure is designed correctly, this additional yield is not going to be gated to specific, sophisticated actors. And then lastly, the more surprising one is that preconfirmations actually open the door to decentralizing block production on the L1 and doing it in a way that is actually compatible with the competitive market that we're in today. So I'm not going to talk much about the first 2 points because they're well explored, so mainly going to focus on the latter two. So starting with additional yield and specifically also keeping in mind the learnings that we've made through PBS. And so the goal with PBS was essentially the same thing, democratize access to additional yield, which is MEV, outsource block production to these specialized actors, and then basically require stakers not to be sophisticated but still having access to this additional yield. But the problem was, so it was very successful in doing that, but then the thing it was not as successful doing was maintaining oversight. So then block production became a centralizing force or a vector, specifically around censorship and a few other properties. Now, when designing this entire market structure from the beginning, we had these key learnings in mind, and from day one, started designing things in a way that the proposers still maintain oversight whilst delegating. So you basically have the best of both worlds now, where you do have access to this additional yield, and you do not require any sophistication, but you have like the whole entire proposer set that is very much decentralized, still being able to express their view, and hence maintain oversight. Now, how is this done in practice? So there are like three main points in which, through which proposers still can maintain oversight, or accountability, so to speak. And the first point is constraints verification. So I see a lot of familiar faces that are familiar with the preconfirmation movement and like how things work, but just quick TLDR, when you issue a preconfirmation, you're basically committing to a transaction ahead of time, and then that is essentially a constraint on the block. And so when the block later gets constructed, you have an aggregation of these constraints, and essentially the block constructor, or the builder, so to speak, is no longer the sole entity building that block. And these constraints get passed down to these actors that then do the block construction process. But with the current system design, the proposer can actually verify, without getting access to the payload, that these constraints are actually adhered to when the block was constructed. So this essentially allows the existing pipeline to exist without much change, but again, giving now more power to the proposer and the capability to ensure that like these constraints are, for example, adhered to. Second point is these delegatees, or these actors, specialized actors that are able to issue preconfirmations for proposers, are staked actors. And we have two types of faults, so safety faults and liveness faults. But specifically for safety faults, these specialized actors can be slashed already with the current system design. So with liveness faults, it is a little bit more tricky to attribute the cause of, let's say, renege issue. But for safety faults, this is actually already working. So a very nice property. And lastly, the third constraint is basically that you want to be able to guarantee, for example, uptime or responsiveness of these delegated actors, which is actually a very hard problem to solve for. But by having like the entities that communicate between the user who's requesting preconfirmations and then the issuer, which would be like a gateway, for example, in a trusted compute environment, you can basically verify like what the responses from these delegatees are, and thereby again like covering a lot of like additional oversight factors and really constraining what these like specialized actors can do. Now the other point, which is actually even more interesting, is the fact that preconfirmations basically now enable multiple parties to collaboratively build a block. And this is possible without having additional feedback loops or adding latency to the system. And I'll elaborate a bit. So this is basically on a very, very high level what block production looks like today on the L1. You have this monolithic builder building the entire block and then basically making it available through the relays to the proposer. But with preconfirmations and these constraints that have been basically merged into existing supply chain pipelines, the proposer, for example, is now able to express, like, if there are, for example, mempool transactions that they want to make sure are included in a block, they can just set them as a constraint and communicate that to the builder. And this actually already works today on the test nets, where some teams, for example, have built an inclusion list module, which is opt-in. And by running this module, basically proposers scout for transactions that might not be included in a block, communicate into builders, and it is basically a validity constraint that is put on the block. But in addition to that, you don't just have the proposer that can issue these constraints. You also have the actual gateways or these entities, these specialized actors that are issuing preconfirmations. And this doesn't necessarily have to be a one-to-one exclusive relationship. You can basically delegate a sub amount of gas, let's say 5 or 10 million gas, to a specific entity, and that entity can, within that gas constraint, issue, again, preconfirmations. So now the block looks like this, where you have the proposer constructing parts of the block, a gateway constructing parts of the block, and the builder basically merging everything together. And as I said, you can have multiple of these entities, and you can multiply that by X. And so at the end of the day, you now have a somewhat very efficient market where you have multiple entities like merging all their constraints together and then constructing the block collaboratively. And the really, really nice property here really is that this is all compatible with the existing supply chain. So this is not like super complicated system that we have to design and might go to production in a year or two. This is actually already live. So just a very high level overview. I'm not going to go into the details. I think this has been discussed in some other talks as well. But essentially, the existing supply chain is from left to right, where you have proposer, relay, builder. And now you have like this additional entity gateway on the side here that interfaces with users requesting preconfirmations. And again, if we think about the previous slide, you can basically have multiple gateways issuing these constraints. And reusing the existing pipes, the proposer can delegate to multiple parties via the relay. These parties can all push their constraints to the relay. The builder then listens to the streams of constraints and takes them into account when constructing the block. A slight change to the block submission itself is just an inclusion of a proof that these constraints are actually adhered to. And then the proposer just ingests the header with the proof and can verify that these constraints are also adhered to before committing and receiving the payload. So overall, very efficient, and you have the compatibility existing, essentially with the existing PBS supply chain. So just to summarize that, you essentially have decentralized block production through preconfirmations, or preconfirmations sort of ushered decentralized block production into existence, even though that was actually not the intention, which is quite nice. Secondly, unlike with PBS, from day one, the proposer has oversight, and not just oversight over the new delegatees, which are the gateways, but you actually now have oversight over block production itself as well, which is a nice factor. And with delegation itself, you have this nice property where you can stay very simple, don't need to run any sophisticated infrastructure, but you do have access to this additional yield. And a final point that I would want to make is basically the combination of delegation plus the oversight creates a market structure where you can now have like very efficient and competition amongst proprietary actors. So the ecosystem can now leverage like these efficiencies that these like sophisticated actors bring to the space, while maintaining the properties that we are here, like that, and that we care about, which is decentralization, censorship resistance, and all of the above. And with such a market structure, you can now have super efficient, let's say, sequences or sequencing services offered by the L1, and make them available to the entire ecosystem. So just to showcase what is possible with such a setup, we prepared a little demo. And so we actually are working on an open source version of a gateway, which we'll release in the next couple of weeks. And we coupled this open source version with our proprietary simulation engine. And just to showcase how powerful such a market structure can be, I'll give it to you now, Lorenzo, to talk through the details.
Hey. So what we're going to see now is a demo of a sequencer or gateway that we've been running on the Helder testnet. And Helder is a testnet that we've been running since July, just to test all the preconfirmation protocols and inclusion list as well. The specific gateway is working for a Tycho stack rollup. So I guess everybody's familiar with Tycho, but they've been really at the forefront for base sequencing. And this is more or less the architecture. So you can imagine you have, in L2s, you have a gateway which for a few slots has the exclusive right to advance the L2 state. And during those slots, it needs to receive transactions. So there is an RPC service that is what users send transactions to. And then the RPC forwards those to the sequencer, which turn is to sequence. And then this is the internal architecture of the gateway. So there's let's say the sequencer, which is really the key part, which decides the ordering of the transactions. And the sequencer then uses a simulation engine just to, I guess, do simulations. And then once those simulations are done, the block is constructed. And once the block is built, then that gets sent to a proposer module, which aggregates, for instance, builds a blob, does the compressions, and then is responsible to land those on the L1. And initially, what we had in the first iteration was a Geth, let's say Tycho Geth as a simulation engine, which I guess was very slow because we had to move all the simulations back and forth to Geth and back. So I think one simulation was around like 1 millisecond, and then sealing the block, which is what you do after you have all the transactions, so computing all the routes, state route, transaction route, receipt route, was around like 20 or 30 milliseconds with just a couple of transactions, so very slow. So what we did over the past couple of weeks, we swapped out the Geth with our internal EVM, so which is built in Rust and could be coupled more tightly with the sequencer. And so on a consumer grade, let's say PC, we reach some, let's say, very high performance levels. So 1600 100,000 transactions per second, which is obviously very high and is like a, say, idealized setup, mostly transfers. So, but still it gives you the idea of what kind of performance you can reach. And again, the idea is that this will be available to L1 proposers that do not directly operate those, but they delegate to parties which can then operate on their behalf. And yeah, and I think which we did, let's say, as a architectural or optimization is very important when you build performance systems to think about how the data flows through the system and the different pipelines. And an interesting one is the block ceiling time. So when we were doing all these transactions per second, you reach the end of the block and then you had to compute all the routes. For instance, one is the transaction route, which takes very long because there were a lot of transactions. So in the first version, it was taking around 500 milliseconds, which basically means that you're spending half your time just doing stuff that is not exactly sequencing transactions, just ancillary stuff you had to make. So what we did instead is and this was all on a single core. What we did instead, we split the work in two. So now there is a simulator core that does the simulations, but in the meanwhile, we're pipelining all the work. So the sequencer, while the simulator is doing the simulation stuff, the sequencer will already start computing these routes, so transaction route, receipt route, and then this is how we managed to bring down the ceiling time to just a couple of milliseconds. So you're spending like most of the block sequencing transactions, user transactions instead of overheads. Now, yeah, first of all, what we're gonna see now is, I guess, the live demo. So we have the gateway up and running, and then we're gonna start a spammer, which is gonna just push a ton of transaction through through a channel, and then ready to be simulated. And we have an internal, let's say, tool that we use to monitor this kind of dashboards live. It's very useful for debugging. So that's what we're gonna see now. So it's gonna start very soon. Yeah. So what's happening here is basically there are two main parts. The panel on the left is the execution preconf latency. So basically when the transaction is received, after it's being simulated and the transaction received is ready to be served to the user. So this is in the order of a couple of microseconds. So obviously it can be very fast, and then after a couple of microseconds, let's say the sequencer overhead, the transaction receipt is ready for the user, and the user knows where it is on the block. And then instead on the right, we see how many transactions we're sequencing, let's say, per second, and the correspective, let's say, gas amount. So as you can see, it can be quite high. And let's say my laptop is not even charging, so maybe the performance is not even great. But I can also crank this up. So now I'm increasing the spammer, and as you can see, this goes up quite quickly. So probably can reach, I think my laptop 300, okay, 160. Anyways, it can be very high. And yeah, this is more or less it. Yeah, that's it. Questions?
Just a quick question. What is shared about this? Like you just, was it just a single roll-up input, or was it multiple?
So this is just showcasing like one isolated gateway and all the sequencing capabilities. So when you say shared, do you mean like in parts of the block construction process, or
Amongst rollups, right?
amongst rollups? Okay. Yeah, so this could be opted into by whatever base rollup would want to use the services, right? So as a base rollup, you can sort of say here's an opt-in. So as a proposer, you want to opt in to sequence my rollup. And then you can also have conditions, for example, like, so if you want to guarantee a certain UX, for example, you might want to say, you can opt into sequencing my rollup, but I would only allow you to opt in if you maybe delegate it to certain parties that guarantee like uptime.
I guess one additional point is that when you are sequencing multiple rollups, you're kind of bound by the slowest of them, right?
Yep.
So you really want to crank up performance as much as possible. So when you're sequencing, let's say, 100 of those, you can still build very good blocks, and you're not bounded by. Imagine like I have to sequence like 5, and one takes like 1 second. That's not very good. So you want to just have very good performance across all of those without too much difference.
So I have two questions. One is, if you are a rollup that's wanting to be based, like, would you be running your own gateway? So you speak to the proposer.
No. So I guess the idea is to basically dedicate or outsource the sequencing to the entire proposer set, but like you can have some controls, or you kind of, as a rollup yourself, you can decide what kind of guarantees you want to have from opting into this, right? Or allowing someone to opt into sequencing on your behalf. And so and this is basically what I meant previously, is like you can say, for example, you are allowed to sequence for me. So if you opt into me to sequence on my behalf, but then you need to guarantee certain, like, let's say KPIs or whatever it is, or certain metrics that you want to guarantee. And so you could, for example, have a short list of, like, let's say 10 gateways that you're like, okay, these match these conditions, and any proposer that opts in can delegate from these set of gateways. And then the proposers basically serve as a police force to make sure that like these gateways or these like well-resourced actors behave like they're supposed to. And for that job, basically, they receive also part of the yield.
And so I guess payment-wise, like, you know, if I am running something through a gateway and I want, like, I don't know, certain position in a block, who is the idea that the gateway is paying to the proposer for that, right? Or
yeah, so that depends on the rollup. So some rollups might want to have a certain like sequencing algorithm, like first come first served, because that's the status quo. Another rollup might want to have like ordered by like gas payment within like a certain like time chunk. So each rollup can also sort of dedicate or dictate like what kind of sequencing like algorithm they want to apply.
My question is more about gateways. So this scheme introduced gateway as a centralized trusted entity, right? So
not trusted.
So my question is, for example, some wallet chooses to use one gateway, right? For example, or
so no. So you have an RPC, like if you want to,
yeah,
and you kind of send your transaction to this RPC, right?
And the RPC sends to the gateway.
Exactly, but it's not necessarily one gateway. Like based on like the proposer schedule and who the proposer then delegated to.
But let's say that one gateway is adopted, right? It could be that, right?
It could,
so the
yes.
one gateway is adopted, as mostly we have the same market structure with RPCs, right? Wherein Fur is vastly dominating and receives most of user transactions. So it could be that one gateway will also dominate this.
But just on the RPC has nothing to do with the gateways, right?
Yes,
so
but RPC can choose gateways.
Yes, no. The RPC, based on the proposer schedule, will choose gateways based on who the proposer dedicated to, right?
So it could be that proposers delegate most of the proposals will delegate to the same gateway.
Yes.
And so exactly. My question is there a possible scenario that gateway will be gateway basically has all the builders' endpoints, right, to send their constraints to these builders specifically, right?
So the gateways send the constraints to the relay.
To the relay.
Yep.
Okay, and relay resends to all builders that participate in this relay.
Yep.
Because my concern was if this scheme might introduce a problem where new builders cannot participate in that because they wouldn't be sent these constraints, and so they wouldn't be able to comply with them, basically.
Yeah,
Because you're now like sending to lots of these entities, and they choose like to which builders they send these constraints.
So in general, it's kind of like the PBS part, so the builder part is still trusted, like right. The new parts that are being built now with gateways, you actually have more oversight. But like so, and it just so if you send your transaction to a builder today, like there are some trust assumptions, right? Like for example, if you send a bundle, that you don't get unbundled, right? So,
yeah, my question is.
And based on that, I'll get there. So, based on that, when you send your transaction as an originator, you can basically, and you communicate with the gateways, you as an originator, just like, for example, Flashbots Protect, you say these, I want to, once they actually end up being sequenced or the block is being built, they should these constraints should only be like streamed to builders that I approve.
So if there's a new builder wants to join the market, to which entities it should go to start receiving these constraints and comply with them?
So the connection will always be the relays, right? But then the relays will distribute based on like what the users say.
Okay.
I think we're pretty tight on time because we've got a surprise stage literally now. So is that one more question, maybe? Anyone? Or no? I'm being told no. So sorry, thank you guys.